Hi everyone, welcome back to the digital electronics pracs that we're going to be going through. This video will be at Schmitt triggers, which is on your prac book on page 9. So in this circuit we're going to be building this thing. Now that 1 meg ohm variable resistor there, or potentiometer, so that's a symbol for potentiometer, that's something that looks a bit like this. It should say B1M on the top, and it'll have 3 pins and a knob that you can adjust the resistance with. Okay. And again, we've got our 4011 IC and LED. So I left my IC in after the first prac because I didn't need to change anything here. And I'm going to connect up my output first. Doesn't matter which order you do it in, I'll put the output on first. And I'm going to be using pin 4 for that output. So 1, 2, 3, 4. And LED. Just like we did in that first prac. Okay. And with my potentiometer, I'm going to be using the breadboard plugged in like this. I find it easier to make the wire connections first, because otherwise the potentiometer gets in the way a little bit. And also I can sort of bend them down, flatten them out of the way. And also notice that they line up every second hole on my breadboard. Okay, so bending them down just to keep them flat out of the way. And the 2 outside pins, and it doesn't matter which ones you connect, as long as each of the 2 outside pins, which correspond to that pin and that pin of my, so these 2 here are the outside pins on the potentiometer. I connect those to positive and 0 volts. The wiper, which is the middle pin on the thing, we're going to be using that as to give us our output voltage here, or input voltage rather. Okay, so configuring my my logic gate, I'm tying the inputs together on both of them. So just using my breadboard wire here to do so. So pin 1 and 2 are tied together, pin 5 and 6 are tied together, and you notice here that it's sort of behaving erratically, and that's because we have this issue of the floating inputs there. They're not connected to anything yet. And the output of the first gate is connected to the input of the second gate here. Okay. So effectively we've got 2 inverters connected together, and a configuration like that's called a buffer. So a buffer just takes and interprets a voltage on the input as either logic low or logic high, and then it gives an output that is an actual digital logic level of like positive, close to positive or close to 0. And so now I'm going to connect up my potentiometer's output, so the middle pin of the wiper of my potentiometer, onto pin 1 or 2, doesn't really matter. And you can see here, now I've got myself my circuit set up, and if I adjust the potentiometer, I should be able to make it turn on and off. And it shouldn't brighten or dim, it should be either on or off. Which just makes sense because these are digital circuits. Digital circuits only have 2 output voltages. This corresponds to on or off. Okay, so if I crank it all the way up this way, LED's off, I should be able to measure that as between the negative and the input pin. So negative in pin 1 in this case, and I'll do that better. That's 0 volts. Okay. Now I'm going to adjust it and keep increasing it, and well, it doesn't really have to be spot on exactly 4 volts on the input there. close enough is good enough. And you notice that the output voltage, it's logic low and it's still 0 volts. Okay, so there's the output voltage there, 0 volts. So as long as the LED is off, we know it's going to be 0 volts. Okay, so it doesn't matter what voltage the input is, the output is going to be 0 if the LED is off. Okay, now I'm trying to capture here the point at which it just turns on. Okay, now it sort of looks like it's flickering there a little bit. That's probably because there are a few instabilities in this thing, but for the most part it's probably flashing more than being dim. And the input voltage there is about 4.1 volts. Okay, so the voltage that it just turned on at, we saw that on this one, is about 4.1 volts. So 4.1 volts. And the output voltage, 0 volts on all of those. And now, if it's on, the output voltage, well, this is what we expect it to be from the first experiment. It should be about 6.3 volts. So, yeah, we're getting close enough to 6 volts. Okay, 6 volts on the output voltage there. And if I keep increasing it, change that input voltage, you can see that at 5.2 volts, the output is still, get it right, still about 6 volts there. Okay, and it doesn't change. I keep increasing that as far as it can go. So now my input's 9 volts and my output is still about 6 volts. Okay, so it doesn't change as I keep increasing it. So first part of my table here, increasing the input voltage from 0 through to 9, it suddenly went from 0 volts on the output to 6 volts on the output when the input was at 4.1 volts. Now we're going to do the same thing but just in reverse. We're going to keep decreasing this. And okay, so it's just flicked off there. If I measure that voltage there now on the input, you can see that it's about 4 volts, which is pretty much exactly what we had before. There's going to be subtle differences, but there's no real actual difference there. And so we saw that the output didn't change until we got to about 4 volts again. Okay, so decreasing the input voltage, the output suddenly changed at about 4 volts to 0 volts in the output. Okay, so if I were to graph what this looks like, here's my input voltage on the horizontal axis here, and we're going to be increasing it. And you can see that as I increase it, it starts off at 0 volts, and when it gets to 4.1 volts, it suddenly changes to 6 volts on the output. And then when I start to decrease it again, going this way, now it stays at 6 volts until I get to about 4.1 volts, and then it suddenly changes back again to 0. And it stays that way until I want it all the way back. And so you can see here we've got this very sharp step here, and critically for this, whether we're increasing the input voltage or decreasing the input voltage, the voltage that it changes at, which we call the threshold, is the same. Okay. It's also around about half of my power supply voltage, so 4.1 volts or 4-ish volts is close enough to half that I don't really mind. Okay, so question 4, you can see that we can sort of do this by hand now. You can see that in order to make the LED switch on and off, I only having to change it just the tiniest little bit. I'm not having to change that potentiometer very much at all, and it goes from completely off to completely on. Okay, and that the position of my potentiometer, it sort of corresponds to the difference in that input voltage, and you can see there's not very much. Okay, and so relating it to the graph above, or this graph here, so this is changing my input to here. You can see that not very much change is required to go from completely off, which is 0 volts on the output, to completely on. Okay, so that graph there is extremely steep at that point. Okay, now we're going to do part 2 of this experiment, which is adding a feedback resistor of a 470 kilo ohms in value. Okay, I don't have a 470k, so I'm going to use 100k instead. We'll still demonstrate the principle. So the values that you get will be a little bit different if you use a 470k. And probably actually mine might be more exaggerated, so we'll see. So connecting the feedback resistor here, so from the output through to the input. Okay. So that would look something like this. Okay. So there's my feedback resistor connecting pin 4 to pin 1. And now if I want it all the way this way, it's still off, keep increasing it, turns on, but now I have to change it a fair bit before I can get it to turn off. Okay, so this is what you should expect to see. You should, the amount that you need to change the potentiometer to turn on and off again should be a lot more. Okay, so now we're going to do those measurements again. Mine are going to be all over the place, so I'm going to, because they'll be a bit different than the ones that were indicated in the input here. So I'm going to increase it. Oh well, actually, let's measure that now. So you can see the input here, which is just on pin 1, is 0 volts. Okay. And the output is logic low, so that's going to be 0 as well. Increase it, and we're going to increase it until it just turns on. So I'm going to try and record that voltage that it just turns on at. Right. And okay, so it's about 7 volts, 7.09 volts. Okay, so the voltage where it just changes is 7.09 volts. Okay, and if I keep increasing it, you can see that it doesn't change. And the output, well, as I expect, the output would be about 6 volts, like it was before. Now I'm going to decrease it until it just switches off. So going slowly, there we go. And it's about a 0.5 volts, okay? I may have overshot it a bit, let's just double check. Yep, 0.55. Okay, so my data, yours may be a little bit different than this. As I increase the voltage, it was stayed at logic low, so 0 volts in the output, until I got to an input of 7.09 volts. And then as I started to, I kept increasing, it stayed there, but then when I decreased it, it wasn't until I got to 0.5 volts, thereabouts, before it changed back again. So on the graph, it'll look something like this. So increasing from 0, my output was 0, so increasing it this way until I get to about 7.09 volts. Then it very suddenly changes to high output again, of 6 volts there. But now, I'm just going to put an arrow here indicating that this was the direction I was going. Now, as I decrease it, you see that it's not until I get down, all the way down to about 0.5 volts in my case, that it transitioned back to low again. Okay, so the arrow is indicating the direction I've travelled there. Okay. And so what has changed here is it's changed the voltage on the input at which the output will change state on, from low to high and from high to low. They're now different voltages, whereas the previous circuit without this feedback resistor, they were the same. So So the input voltage to change from low to high is different than to change from high to low. And what you will find, and in fact this is probably pretty good, because if you do this with the 470k resistor, what you will find is that your voltage there won't be quite so high. It'll probably be maybe 6 volts. And this voltage here probably won't be quite so low, it'll be maybe 2 volts. And the bigger this resistance, well, we can sort of do the thought experiment. If I make this resistance infinite, well, that's this circuit. And this circuit had no difference. This circuit with smaller resistance has a bit more difference. And my circuit with the 100k resistance, which is even less, has a lot more difference there. So a smaller feedback resistance means a larger difference. One of the things that this is useful for would be if I were to have a light sensing circuit where I wanted to set up the output voltage from some kind of voltage divider with a light sensor on it, and on the input here, and let's say the output was switching a lamp on, so you know, like what you might have in your driveway so that it turns the light on at night time. I don't want it so that any light coming from my lamp, which would increase the light level even if it's only by a little bit on my input here, to then switch it back off again. So if I were to have, without any feedback on the input there, on this circuit, so without any feedback on this circuit, if I had my light level sensor here being somewhat illuminated by the lamp it was switching, then when it got dark enough, the lamp would switch on, but that would then provide just a little bit more light, which would tell the circuit to switch the lamp off, which would then tell it to switch back on again, and keep doing that until the light level from the lamp, or the light from the environment was low enough that the lamp wasn't able to light it up again. Okay, so it might switch on and off rapidly for some time, and that would be undesirable, especially if the switching mechanism for the lamp was some electromechanical switch like a relay, which has moving parts in it, and that would wear out very quickly and be damaged. So adding this feedback in here, it means that it's not until it gets very much lighter that it would switch back off again. So you can sort of think of this input voltage is going to be related to the light level somehow. And so the difference between the light level to turn it off and back on again is going to be required in order to prevent this thing from being able to switch itself back off again. So that's just one example.